Hello everyone. In this part of our lecture on confidence intervals, we are going to talk a little more in depth on the margin of error. We are going to see how the margin of error and the confidence level relate to each other and how they influence the precision or accuracy of our estimates. In addition, we are also going to see that we can improve the precision or accuracy of our estimates by varying the size of the sample we use for our study. So increasing the sample size can improve the precision or accuracy of our estimate. So we will learn how to determine the appropriate sample size to improve the precision and stay within a certain margin of error. Let's consider what the margin of error is in confidence intervals. It is the allowance or bandwidth which is provided to estimate the population mean from the point estimate or the sample mean in this case. Essentially, the margin of error helps determine the end points of our interval. The lower end of the interval is obtained by subtracting the margin of error from the point estimate x bar, and the upper end is found by adding the margin of error to the sample mean or the point estimate. The formula for the margin of error is z of alpha by 2. So we have to find the z value of alpha by 2 and then multiply it by sigma divided by square root over n. Now this particular formula applies to studies on one population mean when the population standard deviation is known. Depending on your study, it will change. This formula is going to be different. But for this study, it is this formula, and then we subtract that quantity from our point estimate to find the lower end of the interval, and we add to find the upper end of the interval. And that's what the margin of error is. It is essentially the distance from the center point, from the point estimate to each end of the interval. And that quantity, whether it's the lower end or the upper end, the distance from the point estimate is always going to be the same. Both e values on either side of x bar is going to be the same, right? Here is presented the formula to calculate the margin of error for studies on proportion. When we try to estimate the population proportion from the sample proportion, the formula that we use to calculate the margin of error is z of alpha by 2 and then multiplied by the standard deviation formula for proportions. We have to use the sample proportion in the standard deviation formula, which runs as square root over p hat times 1 minus p hat divided by n, the sample size. And as you can see in this picture, this time we have replaced the point estimate with p hat because it's a study on proportions, and we have subtracted the margin of error from the point estimate p hat to come up with the lower end of the interval, and we've added it to the point estimate to come up with the upper end of our interval. Here we are going to see how the confidence level and the margin of error affect the precision or accuracy of our estimates. It says here for a fixed sample size, decreasing the confidence level decreases the margin of error and hence improves the accuracy of a confidence interval estimate. So let's see what that means. When we are not given a margin to make an error, then our estimate has to be absolutely precise to the actual value. when we add a margin of error around the actual value, or in this case point estimate, then we are given a bandwidth within which we can make an error, and therefore we do not need to be as precise as we had to be when we were not given a margin of error. So when the margin of error is added, the confidence level goes up. The margin of error, of course, is increased, but the precision decreases. We do not need to be as precise as we had to be when there was no margin of error. Now, if we increase the margin of error, so I'm going to make the confidence interval wider. The endpoints are now stretched. And what happens now is that our confidence level has surely gone up once the margin of error was increased, but our precision dropped even further. We do not need to be as precise. We can be further off from the actual value and still be considered correct in our estimate. So that's what we mean here, the relationship between the confidence level, the error, and the accuracy. I'm going to write that here, CL, confidence level, E for error, and precision or the accuracy. Both mean the same thing here. As the confidence level is increased, the margin of error is increased, and vice versa. As the margin of error is increased, the confidence level is also increased. However, the precision or accuracy drops. As the confidence level is decreased, the margin of error is decreased, but the precision level goes up, improves. Now, earlier we stated that as the confidence level increases or decreases, the margin of error also increases or decreases proportionally, and vice versa. However, there's a way of decreasing the margin of error without changing the confidence level, and that is by increasing the sample size. And recall that when the margin of error decreases, when the margin of error is narrow, the precision or the accuracy is improved. So we are going to learn here how we can find the sample size to decrease the margin of error to a certain measure while keeping the same confidence level. Over here below, they have given us the formula to find the sample size n in the case of one population mean when the population standard deviation is known. Now, this particular formula is derived from the formula for the margin of error. Recall that the margin of error formula was E equals Z of alpha by 2 multiplied by sigma divided by square root over n. If we solve for n in the formula of margin of error, that means isolate the n, bring it to the left hand side and move everything to the right, then we will end up with the formula to find the sample size, which is Z of alpha by 2 multiplied by the population standard deviation sigma divided by the margin of error, and the whole thing is squared. This whole expression is squared, and if we get a decimal value, we should round it up to the nearest whole number. Now, how does increasing the value of n, the value of sample size, decrease the margin of error? This is the formula for the margin of error, correct? And we see over here that n is in the denominator. Now, in any fraction, higher the denominator, higher the value of the denominator, smaller is the resulting quotient, correct? For example, let's look at this fraction 1 divided by 2. Here the denominator is a 2. It is 1/2. Now if I increase the denominator and write it as 1/4, what happens? This whole quotient 1/4, 0.25, is smaller than 0.5, which is a quotient of 1/2. If we increase it further, 1/6, that's even smaller than 1/4 or 1/2, correct? So as we increase the value of the denominator, the resulting quotient decreases, and the same thing happens here as well. When we increase the sample size, then sigma divided by square root over n will become a smaller value, and when we multiply that by the z value, we will get a smaller number for the margin of error. All right, so that is how increasing the sample size decreases the margin of error and hence improves the accuracy of a confidence interval estimate. Now here we are going to go through the formula to calculate the sample size in studies of population proportion. Now recall that the formula for the sample size is derived from the formula to calculate the margin of error, which in the case of proportion goes like this: z of alpha multiplied by square root over p hat times 1 minus p hat divided by n, correct? And once we solve for n in this formula, we will get an expression which looks like this: p hat times 1 minus p hat times z of alpha by 2 divided by e whole squared. Now there's a slight problem with this formula. Because it uses p hat in the formula, recall that to calculate p hat we use the formula which is x divided by n. That's the formula to find p hat. However, we will not know what the value of n would be, because that's what we are trying to find here. We are trying to find the sample size using this formula, but for that we need to know what p hat is, and to know what p hat is, we need to know what n is. So here is a catch-22 situation. All right. Therefore, we have to think of coming up with a workaround as to what value we should use for p hat without using the formula for it. Now there are two workarounds to calculate the sample size in studies of population proportion. The first is to use a guesstimated value of the sample proportion p hat, perhaps from a previous study. If we have an idea what the sample proportion is likely to be, then we can use that in the formula to solve for n. The other option is to use an arbitrary value of 0.5 for the sample proportion p hat. And when we use 0.5 for p hat, then the formula that we get is 0.25 times z of alpha by 2 divided by e whole squared. So essentially, into the same formula, we plug in 0.5 for p hat, and what we will end up with is, so if we choose to use 0.5 for p hat, we will have 0.5 times 1 minus 0.5, which is 0.5 times 0.5, which gives us this 0.25. All right. So in most cases, we just go with the arbitrary value of 0.5 for p hat, and our formula to use is 0.25, which is the value for this entire expression p hat times 1 minus p hat.